Welcome everyone to this section of the course on natural language processing with deep learning. We're going to be exploring how to work with text data in conjunction with deep learning. And this topic is a natural extension of the time series and recurrent neural networks topics that we just discussed, since we'll be using a lot of those similar topics in this section of the course. We're going to be creating a neural network that will generate new text based on a corpus of existing text data. And I would highly suggest that you check out the article called The Unreasonable Effectiveness of Recurrent Neural Networks. We've actually linked it for you as a resource in this lecture. So definitely check it out because we're essentially going through the project that's described in that article. So what are we actually going to do and how will this work? Basically, what we're going to be doing is the following task. Given an input string sequence, predict the sequence shifted forward by one character. So if I give you the sequence HELL, shift it over forward and predict that the next sequence of 4 letters should be ELLO to spell out hello. So the character-based recurrent neural network will actually end up learning the structure of the text. And the example that we're going to be working through is going to use the complete works of William Shakespeare. And what's really cool is that you're going to see the network clearly learn playwriting structure and spacing and things like characters entering and exiting just from a character level. So we'll be exploring that and how this network is actually able to learn basic structure of a much larger piece of text by just predicting character to character. So essentially what we're going to be doing is building a model that looks something like this. We have our sequence of input characters, and notice that we have some input layer where it's one hot encoded, and then throughout maybe a hidden layer or multiple hidden layers, we end up attaching weights to these one hot encodings, and eventually the output layer is going to give us what we'll be treating as a probability distribution for all the letters, essentially giving us the highest probability character that should show up next. So let's go through the steps that we're going to be doing in this project. Step number 1 is just to read in the text data. And for this, we can use the basic built-in Python commands to read in a corpus of text as string data. Note, however, if you plan on doing this with your own text data set, you should have at least a large data set that contains about 1 million or more characters for realistic results. Step number 2 is text processing and vectorization. Since the neural network can't take in raw strings, since you can't multiply a raw string by a digit or a floating point number, what we need to do is we need to encode them as integers. So we'll be doing this for all the characters, not just letters. So things like A, B, C, we'll encode those to each have a representative index number, and we'll do the same thing for punctuation. Even empty space will have an encoding. Then step number 3 will be to create batches. So we'll be using TensorFlow's dataset object to easily create batches of text sequences. So something like hello space M, and then the next sequence that is the target sequence will be starting at E and then go LO space my. So you can understand that the complete sequence should be hello my. So we'll want to use sequence lengths that are long enough to capture structure in previous words, but not so long that the sequence is just capturing also historical noise that isn't relevant to the sequence shifted by one character forward. Step number 4 will be actually creating the model, and we'll be using 3 main layers for our example model in this lecture series, and that is an embedding layer, a gated recurrent unit layer, and then a final dense layer. So the embedding layer, what it does is essentially embeds positive integers or indices into dense vectors of a fixed size. So for example, we could imagine that we have some letter encoded to number 4 and another letter encoded to number 20. And what we're going to do is we're going to choose some number of embedding dimensions, and the embedding layer will actually cast or turn those single integers into dense vectors where there's a number per dimension. And it's up to the user to choose the number of embedding dimensions. And this has a lot to do with the way things like word to vector actually works. After that, we'll work with a gated recurrent unit layer, and that's a special type of recurrent neuron unit we discussed in the previous section of the course. And the gated recurrent unit is like a long short-term memory unit with forget gate, but it has fewer parameters than LSTM as it lacks an output gate. So again, we discussed the gated recurrent unit, and you can review this in the previous section of the course. And then finally, we have the dense layer, where there's essentially 1 neuron per character, and character labels will be one hot encoded, so the final dense layer essentially produces a probability per character. And what's really nice about that probability per character is that means we can play around with what's known as temperature. Essentially, we can play around with the fact where we can actually manipulate the probability drawing and maybe not just choose the highest probability character, but actually assign it where we may end up playing around with temperature so that less probable characters happen either more or less often, depending on that factor. So we'll be discussing that as we code along as well. Then step 5 is to train the model. So we'll set up our batches and make sure to one-hot encode our character labels. And then step 6 will be generating new text, similar to how we generated forecasts in the previous section of the course. But what's really cool here is we'll also show you how to save our model's weights and then show you how to reload that model's weights with a different batch size in order to pass in just a single example. Okay, so let's go ahead and get started. I'll see you at the next lecture where we begin coding all of this out.